Okay, here we are. I'm going to put some stuff together here from the last video. I'll make it a recall, but try and put this all together. So here's a definition we had. A square matrix is orthogonal if its columns form an orthonormal set. Okay. And then there's a few theorems that go along with this. A square matrix is orthogonal if and only if its inverse is equal to its transpose. This is key. You need this for homework and stuff. And a corollary to this is that every orthogonal matrix transform is an isometry. Isometry, which means one. If you take the matrix A, the orthogonal matrix A times X, and you define its length using double bars because it could be out of R2, you just get the length of X. So it preserves length, this isometry. And two, also if you take the matrix A times a vector X times the matrix A times a vector Y, you just get the dot product of X and Y. So it preserves length. This is for X and Y in Rn. This is crucial later on. And then, okay, theorem, one more theorem. A matrix A is orthogonal if and only if its rows are orthonormal. Okay. And one more theorem. These are all from the last video. If A is orthogonal, then one A inverse is orthogonal. Two, this is very helpful. The determinant of A, an orthogonal matrix, is always going to be plus or minus 1. And three, if lambda is any eigenvalue of A, then the absolute value of lambda is 1. And four, if you take two matrices that are orthogonal, A1 and A2, A1 times A2 is also orthogonal. Okay. Now, so that's just stuff from before. So note, the length of a vector, I like to use the term norm, but length or norm, is given to be V double bar. And you know what? I mean, in calculus and stuff, or when you take physics, some people use this, some don't. This is really universal. If you just go like this, you're really talking about R2. So this is just going to be V1 plus V2. But if you're an Rn, it just says, okay, this is going to be V1 squared. Oh, those are squares, sorry. V1 squared plus dot 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 Vn squared. All right. Those aren't vectors, those are constants. Ugh. v1 squared plus vn squared. And this is a really famous theorem. The Pythagorean theorem. Vectors u and v in Rn are orthogonal if and only if the length of u plus v squared is equal to the length of u squared plus the length of v squared. And when we have this oral exam for the final, one of you, or multiple people of you, are going to be asked to show this for the case n equals 2. So you might want to get familiar with this. Okay. All right, so now we're getting to what I want to get to today. Got all the background ready. So definition here. Let W be a subspace of Rn. Okay. If a vector z is orthogonal to every vector in W, then Z is orthogonal to W. Okay. The set of all such vectors So the set of all such vectors that are orthogonal to W is called the orthogonal complement of W, which is written W perp, and that's what we call it, W perp. For perpendicular. Note W perp is a subspace of Rn. I might ask you to show that for an example or maybe even prove it. Okay. So here is example 1. Example 1. Okay. Hopefully this gives you, so it's an example, but it's also very general. So this will give you an idea of what's going on with W perp and W. So we're gonna let U1 down to U5 be an orthogonal basis for R5. Okay. So let Y be C1U1 plus C5U5s. So Y is just some vector, and so Y is some vector in W. Oh, sorry, some vector in R5, not W. I haven't even defined W yet. So U1 through U5 is an orthogonal basis for R5. We're going to let Y be a vector in R5. Anyway, so we're going to write this vector Y. Come on. Getting too excited. So we're going to define W to be the span of two of these vectors, U1 and U2. Okay. And we want to write y as a sum of two vectors, z1 plus z2, where z1 is in W and z2 is in W perp. Okay. And this implies that you can do this, but we're also going to, along the way, show why you can do this. All right, so let's see here. So breaking this up, I'm going to go C1U1 plus C2U2 plus C3U3 plus C4U4 plus C4U5. So that's our vector y. And if we break it up like this, that will be our z1. And we break it up like this, that will be our z2. So what we want to show that z2 is in W perp, right? Because that's what we're asked to do. We're asked to, right? We want this z2 here. We want this z2 here to be in W perp. Okay, so we're left to show. So we wrote y as a sum of two vectors. The first one is definitely in the span, so it's in W. So z1 is in W, just by definition. And now we need to show that z2 is in W perp. So that means that we need to show that z2 is perpendicular to every vector in W. Okay, so let's let little w be a random vector in big W. So W will be A1, W1. Sorry, not W. It's going to be A1U1 plus A2U2. And we're going to dot that with Z2. So now I have A1U1 plus A2U2 dotted with Z2, which is C3U3 plus C4U4 plus C5U5. Okay. So this is going to be A1U1 plus A2U2 dotted with C3U3 plus A1U1 plus A2U2 dotted with C4U4. I don't have quite enough room here, so now it's A1U1 plus A2U2 dotted with C5U5. All right, and it's important to justify this step. Okay. And so how do we justify that? So dot products distribute over sums, right? So what I did is I distributed this guy over this guy with this, and this guy with this. So I went right to left. Okay. All right, so try and get over here as far as I can to the left. Now we distribute again. So we have A1, U1 dotted with C3, U3 plus A2, U2 dotted with C3, U3 plus A1, U1 dotted with C4, U4. These are all not vectors. I keep wanting to write them as vectors, but we're just working with... No, they are. Shit. Sorry. They're all vectors. Bloody hell. It's important to go through this from start to finish. So A1, U1, C1. So where am I at here? Okay, plus A2, U2, C4, U4 plus A1, U1, C5, U5 plus A1, U1, A2, U2, C5, U5. All vectors. Okay. All right, so constants also commute. So now we have A1, C3, U1 dotted with U3 plus A2, C3, U2 dotted with U3 plus A1, C4, U1 dotted with U4 plus A2, C2, U2 dotted with U4 plus A1, C5, U1 dotted with U5 plus A2, C5, U2 dotted with U5. Okay. Now, since U1 down to U5 is an orthogonal set, that's given. U1 dotted with U3 equals 0. So that's 0. U2 dotted with U3 is 0. So that's 0. U1 dotted with U4 equals 0. So that's 0. U2 dotted with U4 equals 0. So that's 0. U1 dotted with U5 equals 0. So that's 0. And lastly, U2 dotted with U5 equals 0. So that guy is 0. And therefore, what's the conclusion? Conclude that Z2 is perpendicular, C2 is orthogonal to W. Which is what we wanted to show. Now, note. Note how long this took me. Notice the detail. Notice the citing of properties that are real and actually doing the properties proper. This is the kind of stuff I want to see on these problem sets, right? Your entire grade is based on that stuff. So don't turn it a bunch of crap that's unjustified, because it's starting to really upset me, and it's not right. So if you want to start seeing a really bad grade on these things, it's going to start happening. Because, for example, if you say the determinant of B equals the determinant of P inverse AP, which is equal to det P inverse det A det P, and you don't put any justification here, I don't buy it. Right? And then if you go switching these around, with no explanation, I definitely don't buy that, because now you're telling me that, or maybe you're telling me that multiplication of matrices is commutative, and it's not. So there's some explanation that has to happen here in every one of these steps, right? So the next step's going to be, right? How come that's legal? How come that one's legal? That one I'll buy. So you get this step for free, that the determinant of the identity matrix is 1. That's how it's defined. But every one of these deserves some kind of explanation, and I didn't really see that. And some of you just went from basically this step to that step and said, "Oh, it's this," which again I'm not buying. So there you go. I'm going to stop here because this is getting to be really long, and there is going to be a second half of this where I talk about the orthogonal decomposition theorem. And so now we're back in the book. I love that other book for the stuff we did before, but I want to stick with our book for this part of it. And so this will be on the next video. And I'm not sure if that will be for Friday. Probably will be. Yeah, I'll make it for Friday. That way today, being Wednesday, the 14th, we can have a chat. All right, see you in a bit.